Later on, he did his postdoc at the Max Planck Institute for Solid State Research, Stuttgart, and KTH, Stockholm. His current interests include the study of energetic materials under high pressures using first principles calculations, quantum materials, functional materials, and evolution of band structure of complex materials. He is a recipient of DAE Young Achiever Award in 2012 as well, a member of National Academy of Science, India, and he was recently elected a fellow of the Royal Society of Chemistry as well. Today is going to be talking about ferroelectrics from phonons. So please join me in welcoming Professor G. Vaitheeswaran.
To visit to IIT Madras after a long time, maybe 20 plus years actually. Of course, last January I was there for this conference on Esther meeting. So, and this is the first colloquium in physics actually. So, I would like to start with how we can understand ferroelectrics from phonons. So, we all have studied about the simple omega versus k relation which we study in solid state physics, and then how, like this talk I will try to say that this will help us to understand even before experiment. Let us start doing the experiments, and as a theoretician I always say that okay, we should try to predict something. Okay, following experiments is one thing which is really good, and then try to reproduce it and then try to complement that. But here I will try to show that how one can try to have a prior knowledge about the properties, especially before the experiments, and then especially these ferroelectrics are like evergreen problem in solid state or condensed matter physics, and then we will try to see how using a, because we all know that the electronic structure is a E versus K relation which we normally study in solid state. Similarly, we can also have a omega versus K relation which we normally call it as a phonon dispersion relation, and then we will try to see that how we can try to understand the ferroelectric polarization in this particular copper hydroxide pristine, and then we also try to play around with epitaxial strain, like a small amount of minimal amount of strain or perturbation, so which will try to improve the properties, and then I would like to conclude. So let me first start with this basic slide. Ferroelectrics is the electric cousin of ferromagnet. We all know that ferromagnets, and then this is a base plate and lead spoon of the south pointer used in China first before the BC, and then we discuss about magnetic dipole moment and then the electric dipole moment here, and then this was Weiss was the first one who proposed this in 1907, which is the ferromagnetic and antiferromagnetic. Similarly, we have a ferroelectric and antiferroelectric, and then say this was the first thing, and then starting point of this ferroelectrics. So now we will go to the next one. So in 16th century, so this Signet, so he is from France and first recorded the synthesis of Rochelle salt from the residues of wine. So they first started preparing. At the time the ferroelectricity is not well established, or even the name was not coined as ferroelectric. So that was the thing, and then in 1912 subsequently Debye proposed that a molecule could carry a permanent dipole moment, and the temperature dependent of their alignment should be comparable to the of a Langevin theory of magnetism. So that is why we told it is a cousin of the magnetism. I messed up. Yeah. So in 1912 Schrödinger first proposed this term ferroelectric, it is in German. In his habilitation thesis that a solid could become a ferroelectric at low temperature if the dipole moments could be aligned. So the ferroelectric term was first coined by Schrödinger in 1912, and then in 1921 subsequently, so the real ferroelectricity, a particular material in which they tried to synthesize, and then this was discovered by Joseph Walsek. Okay, so he tried to again precisely synthesize this Rochelle salt, which is sodium, potassium, carbon, hydrogen, oxygen with hydration, with water molecule, where he was when he was a graduate student at University of Minnesota with this Professor Swan. So this first publication on this ferroelectricity, the real synthesis and then reporting the property, first came in 1921. Fine. So like we know the era of the stone era, steel era, like that. So that is what in 1920 to 1930 this was the first discovery of ferroelectricity in a real system, where they synthesized and showed that okay, this compound is ferroelectric. So and then subsequently in 1930 to 1940 this KDP which is called potassium dihydrogen phosphate, so that came into existence, and then they also had some thermodynamic and atomistic models of explaining the ferroelectricity. Of course the synthesis part is done, and then some theory should be proposed to understand the mechanism behind the ferroelectricity and what are all the driving parameters for the system to go. Is it only because of temperature, or what are all the other thermodynamic parameters like order parameter? Because when you talk about ferroelectric, we will see that there will be a displacive transformation and there is also a order disorder transformation. So then we need to bring our thermodynamics and statistical mechanics which we studied, and then this model started in 1930 to 1940, and then in the early 1940s, so the first barium titanate era it came with high K capacitors started really reported coming up in experiments, and then they tried to in 1950s they tried to have a proliferation, like many new ferroelectrics came into existence from the experimental side, and then 1960 to 70 the age of Eisen's, like they are trying to connect the soft modes. So the moment you see phonons and then the order parameters which are also important in understanding the ferroelectric materials, and then 1970 to 80 so they tried to discuss more about ferroics and then the electro-optics and thermistors, and then in 80s to 90 it is how to make it as a composite, so combining ferroelectric material with others and then making a composite, and then they tried to call it as integrated optics, and then in 1990 to 2000 so they tried to go from bulk to miniaturization, like nano levels, they tried to have them layers and all, size effects, manipulations, and tried to modulate the modes and dipoles. And then came this 2D, the popular 2D ferroelectric materials, which is even now popular, and then they are trying to have a variety of new materials which is having similar to that of 2D materials, and then they are used for this nanoelectronic and energy devices. So this is the development, the historic development from 1920 to till date. Yeah, so now okay, so this is again once again 1920 we started doing all these developments, and then till to, of course this is from the paper in 24, and then they have updated up to this. Now even if you take this scandium nitride, which is a narrow bandgap semiconductor, and then if you try to dope aluminum, okay, in place of scandium, partly replacing, they also see some interesting ferroelectric, and then Bivas Saha from Jain CSR is actively working on the experimental part of this aluminum scandium nitride, which scandium nitride is a simple rock salt type structure, and then if you try to dope aluminum on scandium, then it shows interesting ferroelectric properties, and then of course now they try to see this kind of behavior in several compounds, and then the application wide solar cells, fuel cells, and dielectric capacitors, then solid state batteries, and then water splitting and so on. So these are some of the application, like the corresponding thing how the ferroelectric materials try to connect with the application. So this is what, and then now this is very popular in nitrogen based things, which is not so common so far, because ferroelectricity more tried to discuss in oxides earlier, but now the scandium nitride is also getting attention by the experimentalist. Yeah, so now as I told that the dipole moment, the connection between the dipole moment and polarization. So to be a ferroelectric, a material dipole moment that can be switched by applying electric field, okay, and then for a ferroelectric material the net dipole moment arises from the combined dipole moments within the unit cell. So and then the prerequisite is we need a non-centrosymmetric structure which should lack inversion symmetry, and other requirement is the existence of the local dipole moment, which typically lead to a macroscopic polarization, but not necessarily if there are domains that cancel completely. So now these are the basic things which are a prerequisite for a material to have ferroelectric properties. Now okay, so the tiny dipoles but big impact towards the polarization, and then when it comes for application, people discuss that they have a very good impact on organic photovoltaics, electromechanical actuators, high energy density capacitors, piezoelectric and pyroelectric sensors, and then nano generators for energy harvesting and self powered electronics. So these are this is a recent thing which we took from the ACS applied electronic materials, where we have a nice connection between ferroelectrics for the materials and as well as memory. Okay. So the next one, so the relationship between the dielectric, piezoelectric, pyroelectric and ferroelectric material. Dielectric of course is an electric, you all know that, which can be polarized by application of an external electric field, and piezoelectric is a generation of charge in response to applied stress. I tried to give a stress on this material and try to see. Pyroelectric is generation with response to changing the temperature of the material, and ferroelectricity is obtained when the orientation of the polarization can be reoriented between crystallographic equivalent. So you have a same system but two different crystal structures, and then one can try to take a temperature, which is the basic thermodynamic parameter, to flip the dipoles, okay, similar to what we see in magnetism. So here we can try to do by electric field. Yeah, so now, okay, so the moment you talk about this, we are more concerned about the crystallographic permission for what are all the basic space group criterion which will allow us to have ferroelectricity in some kind of compounds, okay, so which is allowed to be ferroelectric. So now we have 32 point groups, and then 11 are centrosymmetric and 21 is non-centrosymmetric. So these are the compounds which are not of much of interest, and then we have a 2D piezoelectric with one exception, then polar pyroelectric, non-polar, then in this 10 polar we have a reversible polarization ferroelectric as well as non-reversible polarization, and these are the possible space groups. So for a theory person we always try to find out a space group which will favor the polarization, okay. Of course there will be a structural transformation, but then we have to be more specific in selecting a particular space group, because these calculations are computationally very expensive, okay, and then we have to make sure that, okay, what are all the possible, from the literature we will try to see that what are all the possible space group which will favor us for ferroelectric, and then you see these are this non-centrosymmetric polar and non-polar, so for which we have monoclinic, orthorhombic has more, and tetragonal, rhomboidal and axial, these are the corresponding space groups, okay, and then these are for centrosymmetric thing, and then this can also be, temperature is one thing, and one can also try to tune this by applying strain to the particular lattice, and this can be like the ferroelectricity can be triggered, okay, we can try to bring that. Now we will see the next one, okay, so the connection between the polar and non-polar, okay, so then we know all these things, the ferroelectric loop which we have studied in solid state physics, precise similar to what we see the BH curve in the magnetism, and then this paraelectric loop is okay, of course it shows some nonlinear behavior but not so good like this, and then people normally, okay, so this is something interesting which I started learning while doing this PowerPoint. So ferroelectrics go bananas, so often we are misguided by the loop which we see that. So for example, this is a true ferroelectric, nickname banana they call it, and then you get something, a loop which is not a precise hysteresis. So they say the ordinary bananas exhibit a closed loop of switch charges, and then the applied voltage that can nearly misinterpreted as ferroelectric, okay. So one can try to say that it is not necessary that if you get like this then we can conclude that as a ferroelectric, and then several experimental results were also reported like misinterpreted this as a ferroelectric. So I will show one classic example. So this famous article by this people group in 2008, so where they look like this banana, and then these are not, if you have this kind of loop then we cannot conclude that particular system to be a ferroelectric. Yeah, so now no, banana shape, it's not a banana, no.
But that banana compound that you showed was a true ferroelectric, right?
No, it was assumed to be ferroelectric, but then it is not, okay. So one can always be misguided by this thing, that's what there are experimental controversies available in the literature claiming that the person has misinterpreted that particular system as ferroelectric, in reality it is not.
I still didn't get it while he's fixing it.
Yeah, so
That banana compound you
banana type of loop, so that is not a proper ferroelectric, okay. One has to get a precise thing as I showed in the previous slide. So people often say that, okay, this could be a ferroelectric, but then that is not.
Just make
Yeah, please.
So to get that polarization versus electric field,
Yeah, you should get yes.
looks like a banana, is not sufficient
To confirm that, yes, correct.
But we still have a reminiscent polarization.
Yeah, but that is not very good, na, when compared to the precise behavior. So you see, it is like a loop, it's going on, but then it is not like that. I hope it will be okay now. Okay, this, do you need something? I have my own thing. Sorry for this inconvenience. So a member of this fresonite type structure. So and then this has this particular non-centrosymmetric polar space group and they exhibit a 2D like structure. And then here also like, so they get the loop because with this, this is answering to your question because this is not a pakka like BH loop like similarly to the magnetic analog. So and then this is not adequate enough for us to conclude. So that's what the take home message is. So now the next one is this Sivaram's thing. So you take barium titanate, which is MSc level solid state experiment which we all do. So it's a paraelectric at high temperature and it is a cubic structure. So which is very simple, and then try to lower the temperature from room temperature. There is a cubic to tetragonal, then to orthorhombic, then to rhomboidal transformation, and obviously there is a distortion in the titanium atom. Okay, so that is the key player. Okay, so that to try to trigger the ferroelectricity. This is bulk. Okay, so as a bulk, if you have a barium titanate and then try to from room temperature try to lower the temperature, then it undergoes a temperature induced structural transformation from cubic to tetragonal to orthorhombic to rhomboidal, and then you see cubic is paraelectric. So we don't see any polarization, and then as and when you lower the temperature, so the structural distortion happens. There is a this is a displacive transformation where we tried to go from a paraelectric to ferroelectric structural transformation. Okay, so then from tetragonal onwards we started trying to get the signals of polarization in a bulk, and then orthorhombic is much more, and then when it comes to the low temperature thing, so it is very ordered, and then we do see all the dipoles aligned in a particular direction. Yeah, so now the interesting point here is the displacive versus order disorder. So these are the two key players to understand the mechanism of ferroelectricity. So here we do see that the paraelectric phase is microscopically non-polar because we don't expect any polarization in that, and then you have a system which is similar to barium titanate case. So you have a system which is paraelectric cool down, and then we see a ferroelectric phase transformation, so which is purely displacive. Okay, this is lead titanate, barium titanate are the classic examples. Okay, and then there is also another thing which is purely like entropy driven, which is order disorder. So if the paraelectric phase is only non-polar in a microscopically or thermally average sense, and then when you try to cooling down, then you try to get ordered phase. Okay, there are something where the space group changes, and then here, so the disordered to ordered phase. So this is NaNO2 is one such of classic example, and this potassium dihydrogen phosphate is also another example where it is purely order disorder type. This is the example for sodium nitrate, NaNO2, where which is paraelectric, which is a disordered, and then when you try to cool it down, so it goes to ferroelectric ordered phase. So when you try to understand the mechanism for ferroelectricity, these two are the important criterion. One is displacive, another one is order disorder. Yeah, so then okay, then what is proper and improper ferroelectrics? When we discuss about this, these two are the thing. So now we are going to connect it with the soft modes, okay, which I told in the beginning. So how to understand this? By looking into the phonon dispersion relation. So we will see that, so proper ferroelectricity, the soft phonon mode leading to this particular transition occurs at the gamma point, which is the center of the Brillouin zone, and then the soft mode consists of a polar atomic displacement, making the polar mode the primary order parameter driving this transformation. We are connecting it with the order parameter, and then this we can see that, okay, so there is a mode which is trying to become imaginary, and then of course one can freeze that particular mode, and then I will show what we have done, and then we have to compute the energies as a function of displacement or distortion. So now the improper ferroelectrics, so it can account at zone boundaries, not necessarily it should be at the gamma point, and it can be at x, m or r, any other point of the Brillouin zone, and then this occurs when the polar mode is stable in the high symmetry phase, but the softening of the non-polar mode drives it to be energetically favorable at some other point of the k path of the Brillouin zone. So now here the polar mode is the secondary order parameter. So proper ferroelectric, it is only one parameter involved, but here it is more than one, which we can write the free energy expression. So you can see this, the primary order parameter is eta here, so it is quadratic. But then when you try to discuss about this improper, you have a term primary q as well as this order parameter eta, so which is secondary order parameter, both are involved, okay, and then you have a dot product of this, and then this will have a combination, and you can expect the phonon modes to be imaginary or soft at any other point other than the gamma point also. It can be at multiple points, and it be continuous along the Brillouin zone also. So that is what, and then when you have this thing, both this parameter involved, then we call it as a hybrid improper ferroelectricity. So and then this was first proposed in the superlattice, because it cannot be in a single atom or solid. We have a superlattice of PbTiO3 and SrTiO3, then we can have this combination, so effect actually.
But see, all the powers are even Q or eta, but the curve, that free energy curve you have shown in the last page is asymmetric.
Yes,
So are there some?
I will show that later. I will discuss about that in our real thing. So now we will try to see like hyperferroelectrics, like okay. So if you see that when the longitudinal phonons, okay, optic phonon mode is unstable, and then this is more discussed in this lithium beryllium antimony, where we do get, you see, k gamma direction, it's completely coming down, and then this is mainly the longitudinal optic phonon modes. And then why this is hyperferroelectrics are exciting means they can try to make ultra thin ferroelectric films which can be used for this kind of nanoelectronics and memory devices. Yeah, so now coming back to these theories of ferroelectricity, so we have a thermodynamic theory where we try to get the Gibbs free energy power series, and then we also have a lattice dynamic theory which is purely driven by the phonon frequency, the square of course, so T minus Tc, and then we connect it with the soft mode. Now we will see how these two can be linked with each other. Yeah, so why one need to understand the phonon dispersion relation or lattice dynamics? Okay, so now this has a direct link with the volumetric and constant pressure and of course heat capacities, the Helmholtz and Gibbs free energies, the thermal conductivity, then the spectral signature we can try to get from IR and Raman modes, and then superconductivity, especially the phase transition, it could be temperature or pressure driven, and then finally the ferroelectricity. Okay, so and then this is for diamond where we get nice smooth dispersion relation without any imaginary modes. Fine. So then what is the link with the soft mode and ferroelectricity? So is that a signature that okay, there could be a structural transformation in solids when you have a soft mode, and then a collective excitation whose frequency decreases anomalously at the transition point is reached. So this is not only restricted to temperature, we do see this kind of thing even at pressure. So when you try to apply pressure on a system, so the system, the phonon frequencies will try to respond to the pressure, and then we do see soft modes even in that thing, but one cannot expect ferroelectricity there, but rather we do expect a structural phase transformation, okay, which is purely driven by the phonons. It could be infrared or Raman active, both can be identified by using this thing. So now we will see that what is the connection between the soft mode and ferroelectricity. As the temperature is lowered, the frequency of the soft mode approaches 0 until the transition temperature. The mode is frozen in a distortion of the high temperature structure. Okay, so I will show that, and then we also can see that zone boundary as well as in the other K path of the Brillouin zone. Now, these are the fantastic thing which is written by G. Venkatraman in 1979. So when I started doing this particular thing, how the soft mode and structural phase transition were connected. So this Venkatraman started this thing in from IGCAR Kalpakam. At the time it was not even IGCAR, it was Reactor Research Laboratory Kalpakam, and then there he tried to discuss how one can try to understand a structural phase transformation by seeing the phonon frequencies or the phonon modes. Okay, and then subsequently later in 2012 with the same title, so there is another article on soft mode and structural phase transition by Cowley, so in integrated ferroelectrics, and then this is especially for the students if you want to understand the phenomena or the real how the phonon modes are connected to ferroelectricity. So this will be a wonderful article to read.
So the titles are same?
Yes, yes, but then this was in 1979. Yeah, we don't know, but then still the titles are same because I am taken from the journal. Yeah, now okay, so now what is the origin of negative frequencies? So that is an interesting question. So this is for the tin sulfide in the orthorhombic structure. We do see that there is a phonon mode which is becoming imaginary along the y point and gamma point. These two are of interest to us, and then when you try to see this mode and then try to distort it, okay, as a function, and then try to compute the energy, then you get like a double well like thing, and then for the y point and the gamma point, and then subsequently when you try to freeze this particular thing and do the distortion, eventually it will lead to a new space group, okay, which will be ferroelectric. Okay, this particular Cmcm phase group is paraelectric, and then it is a non-polar, and then we don't see any kind of polarization, and then eventually we are doing a density functional perturbation theory, so which computes the phonon frequencies within the harmonic approximation. This has to be taken with a pinch of salt. Okay, so if there are unharmonicity, then also you will get imaginary phonon frequencies. Okay, but one has to be very careful whether it is purely coming from the ferroelectric point of view or if the system has large unharmonicity. So magnesium carbon nickel 3, which is a superconductor which is reported in early 2000. So if you compute the phonon dispersion relation of magnesium carbon nickel 3, it will show imaginary phonon modes. Then it doesn't mean that the particular structure is unstable. Experimentalists could do a synthesis, and then they have measured the X-ray diffraction and then proved that that particular cubic structure, which is anti-perovskite structure, is quite stable for pressure range also, but there is a role of unharmonicity in stabilizing the particular compound in synthesis itself. So that is why here we try to say that okay, by freezing this we do get a non-polar to polar, the space group changes, and then we do see ferroelectricity there. So now what are the origins of the negative phonon frequencies? Of course one has to be very careful with the numerical calculation because we are working with the density functional theory, and then if the material is strongly correlated, and then especially when you are dealing with rare earth or actinide system where the spin orbit coupling, of course transition metals do have considerable spin orbit coupling, so then this will be very sensitive to this, and then a dynamic instability intrinsic to the system being studied, something which could be related to the system, the synthesis point of view also. We need to make sure that the negative phonon frequencies aren't arising from any computational noise, because if the size of the supercell is not adequate, then obviously you may get, this is for the students who are involved in computing the phonons, so otherwise this will give a wrong information about the structure. Yeah, so this is very common in strontium titanate also, like where we try to see that you see gamma, then M, then it goes from gamma to R also. So and then these are the modes 1 to 3 are ferroelectric instability at the gamma point, and then M and R are the rotations of the titanium O6 octahedra which try to drive the system to ferroelectric by freezing these things. And then this utility of these negative phonons or imaginary modes is also very common in halide perovskites, cesium PbI3. Then phase transformation, if the high symmetry structure is known, we can give microscopic view of the atomic movements of the structural transformation. Then the crystal structure prediction also we can do. If the phonon modes are negative, then one can try to see how we can try to evolve to a new structure by freezing that mode. Yeah. So now we will come with this introduction. Now I will try to showcase our recent result, we started taking this copper hydroxide, which is like old wine in a new bottle. Okay, this system has been known since 1960s or something. So we can see that first one was from 1961. So this from German group. They tried to report the crystal structure, which is Cmcm orthorhombic. So this was the first thing in which they tried to report. Then subsequently several people, it is not that it has this particular structure, and then we have another structure reported on this, and then subsequently another, this is a famous mineral called spertinite. It's a naturally occurring mineral, and then it has a CmC21 structure, which is different from the Cmcm orthorhombic, which was reported by University of Zurich group. This was also in late 70s and all. And then there were also a proposal in which they say that this could be a new ferroelectric. Okay, but then this was a proposal, and then they tried to refine the crystal structure, and they proposed that this could be a ferroelectric, but they have not measured the hysteresis loop or tried to get the polarization, nothing. So they just proposed it. So this was the motivation for us to see, okay, whether, and then the interesting point is, so there is also something that this copper hydroxide is magnetic. Okay, and then normally like superconductivity and magnetism, is it possible for us to have a coupling between magnetism and ferroelectricity? So then that we call it as a multiferroic, and then there's a magnetoelectric coupling also present. So that was also another motivation for us to know that what will be the this copper hydroxide magnetic. That is what first we thought, and then we want to know that, okay, this particular proposal from experimentalists came that, okay, this could be a ferroelectric. So this combined effect motivated us to see, okay, can we try to understand this in a much better way? Yeah, so this is the experimental thing, and then it clearly it is reported at low temperature, it orders antiferrometric with 2D like material, but the Néel temperature is very low, 23.5 or 40 to 43. There were reports ranging in this paper, and then initially the space group was determined to be centrosymmetric. So with Cmcm, the centrosymmetry, then we can try to rule out that there is no possibility for that particular system to get polarized. So later the space group was identified as a non-centrosymmetric with Cmc21 forms a deformed 4+1+1 octahedral environment. Then the Cmcm is paraelectric phase, ferroelectric space group is given as Cmc21, and this Curie temperature for this ferroelectric transformation is around room temperature or above room temperature, okay, 343, and then this is a layered system, and the experimental PE loop is not reported. So that is the primary motivation for us to start this, and then the magnetism is also there in this particular thing. With all these things we started our calculation and see how best we can try to address this particular system. Yeah, so since the system is magnetic, and then we made a 2x2x2 cell, we enhanced the Cmcm and then tried to consider ferromagnetic AFM 1, 2, 3, 4 with various kind of, because there is no precise neutron study available. So it is hard work for us to compute, and then this has around 80 atom supercell. Okay, so and then we tried to see that, and then we could see that this antiferrometric one alignment is more favorable in terms of the total energy. Okay, which concluded as, okay, of course we have taken Hubbard U and van der Waals because it's a layered system, all these things, and then we tried to compute this, and then we could see that the AFM1 structure is more favorable in terms of the total energy, which concluded us to proceed with the FM1 structure. The next one, okay, so we started with the high symmetry Cmcm structure, and then we computed the phonon dispersion relation, and we could see that there are 4 branches which is imaginary along the entire K path. So you see gamma, Y, Z, S, gamma, R, something like that, and then so this phonon dispersion, so show that, okay, there are 4 branches which is thoroughly like imaginary going along the Brillouin zone, and then at gamma point this branch 1 and 3 so corresponds to the infrared B1U mode having frequencies of -649 47 centimeter inverse and 336, and then this branch 2 and 4 corresponds to Raman active. Okay, so we have a combination, the infrared and Raman, and then of course this phonon DOS corresponds to the dispersion, and this is computed for the 2 by 2 by 2 cell. So now, okay, what happens? So then we try to freeze that particular mode, and then so this starting point was the structure which Cmcm, and then we have this the gamma point B1u, and then when we try to freeze this mode, so these are the branches, and then this corresponds to CMC21 branch 1, then CMC21 branch 3, then this C2 bar M, and then this C2 bar M. So these are the 4 space group which we got by freezing the phonon mode as a function of displacement. We are trying to move the atoms and try to get the total energy or compute the total energy as a function of displacement, and then we try to have a positive and negative, okay, and then try to get this, and eventually it gave us all the 4 kind of space groups, and then we computed phonons once again in that.
How do you know there are only 4? Because the entire phonon band seems to be negative.
Yes, but that is a K path, but the branch we are trying to freeze. At that particular point, we are trying to take each branch and then trying to displace, okay, and then trying to compute the phonons, and then you try to regenerate the structure and see what are all the corresponding space groups which is giving. So I am trying to address a temperature induced structural transformation which is not possible with normal DFT. Okay, for example, this is a temperature induced transformation. So now I have a structure which is formed at room temperature or something. When I do the phonon dispersion, I do get all the branches. So I cannot capture the physics properly. So now what I am trying to say, I try to freeze the phonon mode. So then I say that there is some structural transformation which is happening. So for example, here paraelectric to ferroelectric transformation. Then I try to take that particular branch, and then we see which are IR active, which are Raman active. Okay, then I try to move the displace and then try to get the total energy for each branch. Branch 1, 2, 3, 4. So then I try to map it with the crystal structure.
So just quick,
Yeah.
all of them at gamma at K0, or you also have them at the band edges?
I will show the phonon dispersion at the entire branch. Please wait. We are trying to get at the, so these are the corresponding space groups by freezing this mode from the displacement. Now the next slide will give answer to your question. So now once again we computed the phonon dispersion relation for the branches in which we did mode freezing, okay, and then this is for the branch 1. You do see there is no imaginary phonon modes, all are real, and then the branch 2 once again you get at the gamma point, at the M point, at the A point, and also at V point. So then we rule out this branch 2 freezing is not going to help me, okay. Then similarly branch 3, if you see, all the phonon modes are real, we don't see any imaginary mode. Freezing the mode, then you once again go back to the phonon dispersion in the entire K path, okay, and then once again when you do for this branch 4, you do see lot of imaginary phonon modes. So now I am trying to rule out this branch 2 and branch 4. So then I say that, okay, and then this branch 1 and branch 3 will be a potential ferroelectric, because I am trying to get the phonons which are, now we have to calculate the polarization, because this is not the end of the story. So once again we try to compute the polarization.
That is just a small.
Yes.
So if you go back, the displacements, are you displacing all the possible atoms, showing that phonon mode?
Yes, yes, yes. Otherwise we cannot get the entire phonon dispersion relation, because I do that, and then first thing I will get the space group and the CIF file. Okay. Then with that CIF file, I have to once again compute the phonon dispersion for the 2 by 2 by 2 by 2 cell in this particular space group. Then I will get the entire dispersion here, and I want to see that, okay, whether I am able to have a stable structure without any soft mode or imaginary phonon mode in this particular space group. So this is like a group subgroup transformation I am trying to search from one space group by slowly moving the atom with the displacive transformation.
Branch 1 and 3 are giving the minimum.
Yes, 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 yes. And then this branch 2 and branch 4, although I have a new space group, but I am not going to get benefit out of it. So I am ruling out the possibility, and our interest is, okay, let me see whether we can try to get a decent polarization which is sizable and non-zero, and then from this branch 1 and branch 3. So now we try to compute the polarization again as a function of displacement, because as I told, this is a displacive transformation. This is simple. By moving the atoms, we are trying to calculate the energies and then see how it compares with the original energy, and then taking the difference, and then for each displacement we try to, because we are doing it for positive and negative displacement. and then we could see that this branch 1 and branch 3 here. So we saw that branch 1 they are trying to have a compensation of each mode, and then it is mix up of up and down, so it is not very sizable. But whereas in branch 3 has a large polarization, as all the dipoles are up over the polarized sums, because we have to sum up all the dipoles. So now branch 3 is a potential thing when compared to branch 1. So that's what we conclude from here. And then okay, so this is again copper is in 2+ state. Okay, you always have the doubt, I know that. So and then it is a D9, na? And then they say that of course this article in Chemistry of Materials which appeared in 2011 is also showed that okay, the distance really matters between the copper and oxygen. Okay, and then we see that the branch 1 is relatively having 0.88, but the branch 3 where the polarization is relatively large has a 1.11 larger thing. So we are trying to connect this. Okay, so this distance is also responsible. I will not say that's the only thing which is responsible, apart from freezing the phonon mode and then trying to get a new space group. Of course, this is a structural phase transition from a paraelectric to ferroelectric, and this Jahn Teller is also having a added advantage. Copper is in 2+ state here. So that also we concluded. Then we also tried to compute the Born effective charge tensors, where we tried to apply a field and see how the system is getting polarized, and then we see that copper 2+ doesn't change much. 2.28, 2.28, all these things. So if there is a drastic thing, change or enhancement, then we cannot call it as a geometric ferroelectric. So here the change is not so like alarming, so which made us to conclude that this is a proper geometric ferroelectric. Yeah, so then we tried to compute the band structure and see, okay, all these high symmetry and then the low symmetry branch 1 and branch 3 are found to be insulators. We have taken care of the correlation effects because of the band gap is always a problem in density functional theory. So all those things have around 2.5 to 2.7 EV band gap. Okay, so it's an indirect wide band gap semiconductor. That's what we conclude. Then what will happen to the strain? So now I identified a potential ferroelectric phase. Now what will happen if I try to apply strain on this particular system? Okay, whether the strain can do some wonders, or because this is to complement the experimental, because they always have a substrate which will have a strain on the real material, thin film which they deposit, like strontium titanate, like substrates. So now we are trying to mimic indirectly the same substrate strain to the lattice. Okay, and then this we know from the literature that this epitaxial strain is very important, and then several papers by Nicola Spalding and others, they have already shown that the epitaxial strain can tune or enhance the ferroelectric behavior of a system, especially in solids, to a greater extent. So that's what we tried to do that. So then we tried to have a with respect to epitaxial strain, and we are trying to take branch 1 and branch 3, because branch 2 and 4 is not of interest to us, and then we tried to have a positive and negative value of strain, and then we tried to see how these lattice parameters behave with respect to strain. Okay, so this is what the epitaxial and the biaxial strain we say, both compressive and tensile. I will show how the polarization. So this alpha phase Cmc21, we have a quadratic polynomial fit, and then the polarization behaves in this way, and then for the other thing it is going in it is trying to start from 46 and trying to decreases. Okay, for this this phase which is already 42 or something. So now they both have a different kind of behavior, but so they have a this quadratic kind of behavior, polynomial fit for both the things, and then the spontaneous polarization is coupled with the strain tensor, and then we also have a linear piezoelectric coefficient because it's a strain dependent, and then we also have a quadratic piezoelectric coefficient. So then we try to look into that also, and then what is the origin of this non-linear polarization with respect to the strain, and then now here we try to see for each atom specific. This is answer to your question. So we try to see how we are trying to, when you apply strain to the system, each atom will respond to that, and the interatomic distance will be varying between the atoms and on their own. So now we try to do with respect to the atomic displacement and strain, in the alpha phase the polarization is doubled under compressive strain. Okay, in the alpha phase this oxygen and hydrogen have a significant vertical shift, nearly double under compressive strain compared to the tensile. Okay, and then this 5% plus 5 to minus 5 supporting the observed polarization values. In beta phase the oxygen 1 hydrogen 1 atomic displacement dominate over their displacement. Note that this oxygen 1 hydrogen 1 oxygen 2 hydrogen 2 pairs in the beta phase exhibit opposite displacement. It is not necessary that all atoms will respond in the same way. So one may try to move, other will try to compensate also. So that is what is happening, leading to a polarization cancellation to some extent. It is not, the beta phase is not so good like the alpha phase. Yeah, so then we also tried to, because we are playing with strain, we tried to get the piezoelectric stress tensor EAJ. It is defined by the polarization in I direction arising from the strain coupled with that particular direction. So in conventional piezoelectric the longitudinal E33 and the transverse E31 coefficient typically exhibit opposite sign, but in electric oxidizing materials they have the same sign. Okay, here both the components alpha phase have opposite sign, but in beta phase they have the same sign. That is what, but still this needs experimental confirmation. So then we also try to see that, okay, what will happen if we apply to the strain, what happens to the electronic structure. We see that for a material to prevent the current leakage, that particular material should remain semiconducting, because when you try to apply a strain or pressure, we do see a semiconductor is becoming metal and eventually it may also become superconductor. Pressure can tune like strain versus pressure. So now in this particular, since the band gap is relatively large, so we try to see the electronic structure at all these things, and then we could see most of this strain thing starting from plus 5 to minus 5, the systems remain semiconducting and we don't see a change in the electronic structure of the system. So finally I would like to conclude, I am close to 5:30. So from the high symmetry Cmcm structure we identify 4 polymorphs by mode freezing of the 4 modes, and then B1U mode leads to the ferroelectric, which is the Cmcm2. This is the problem for the experimental, because one has to do infrared, because this is not Raman. Okay, so here we could conclude that this B1U mode is the key player for driving that particular material. That is the bottleneck for the experiment, because normally experimentally they measure Raman. Okay, if you do a temperature dependent Raman, for example, if it is a B2G mode, and then if one does a temperature dependent Raman, then you can see a shift in the peaks which will correspond to the softening which we see in this phonon. But here it is B1U mode, so that is why experimentally should try to look into the, because for infrared I think they need to look into terahertz kind of measurements. That's what I am not expert in that. So and then these 2 ferroelectric phase show different degree of polarization due to different structural distortion, and then apart from the structural distortion, based on these distances we do see that the Jahn-Teller kind of distortion plays an additional effect in addition to the structural transformation for enhancing the ferroelectricity in the copper oxygen bond distortion in the octahedra. These 2 different structure with identical space group could stem from incommensurate to commensurate like phenomena. However, this is only a hand waving argument. I am not trying to confirm because this needs experimental confirmation. And then the stable ferroelectric phase are indirect wide bandgap semiconductors. Both alpha and beta phase, the polarization and EG shows a nonlinear behavior as a function of strain. This is purely the effect of strain. And then this compressive strain influence electric polarization more strongly than tensile strain, and the band gap is narrowed in the ferroelectric phases by epitaxial strain, but the compound still remains semiconducting. There is slightly lowering in the band gap, but then it doesn't make the, if it become metal then it will not be a ferroelectric also. So that is what. And then of course Subhajit Sav and Anurupa and Kanchana were the real key players, and then of course we did this in collaboration with Andres Camilo from University of Santander in Colombia. And then I would like to acknowledge Institute of Eminence, University of Hyderabad for supporting this, and then CMSD for the facilities, and of course most of the calculations were also done in HPC in Hyderabad, CDAC and NSM. So Anurupa is supported by Inspire, and then Subhajit is supported by MOE for fellowship. And then this is the, last year we published this work proposing these ferroelectric polymers, and then subsequently just last week this paper got accepted where we tried to show the epitaxial strain effect in the ferroelectric polarization. Thank you. So this is the University of Hyderabad campus. We do have a lot of deers, peacock, and then if you go to very high, larger strain rates, then you may just the symmetry will be lost. So then there is no guarantee that experimentally it can be realized. But interesting point in this thing, most of the systems is Raman modes, they drive the ferroelectric. So, but this is one rare example where we do see the infrared modes, they drive the ferroelectricity. That's what, and then I am sure it is very difficult for the experimentalist to identify this unless until they do some infrared thing and try to capture that. So otherwise it is, if it is Raman, then it will fascinate everybody. This is a semiconducting thing, especially for to answer to your question. If it is metallic, the scattering will be very poor. Okay, experimentalists who want to do Raman, they prefer gapped systems where they can try to get the clear signals of the Raman, and then this is quite interesting for them.
Okay, so if there are no further questions, we can conclude the session. So I'd like to call upon our respected HOD sir for presenting memento to our guest speaker.
Yeah. Thank you. Hey, you please take a picture. This is a proof that I came and delivered a talk. Thank you. Thank you very much. Yeah. No, she has not taken the picture yet. Ah, yes. Please. Thank you. No. Yes. Thank you.